Hello everyone, today we'll be solving HackerRank Gemstones. Now, this question is really, really trivial, I guess, if you want to put it that way. But I think there's a really good Bitmask implementation that will effectively teach you the basics of Bitmasks and start to make you think about how you can use them in other questions, which is why I'm making a video on this because it's going to be very useful in the future. This question will teach you the basics on some basic Bitmask functions, how to manipulate Bitmasks, and one of the key things you can do with them. After this video, you should, understand Bitmasks a bit more and start to be more comfortable and familiar when using them in your question, in solving your questions, and learning Bitmasks early or learning them will help you a lot more when you get to more advanced problems, either requiring DP or so on. So let's read the question, Gemstones. There is a collection of rocks where each rock has various minerals embedded in it. Each type of mineral is designated by a lowercase letter in the range ASCII A to C, so it's all lowercase. There may be multiple occurrences of a mineral in a rock. A mineral is called a gemstone if it occurs at least once in each of the rocks in the collection. So if a certain letter appears in every single rock, it is considered a gemstone. So as you can see, B and C appear in each rock, so there are two gemstones. And we're just asked to display the number of gemstones in the collection. In the end, I'll briefly explain how you would go about writing the code to see which ones are the gemstones. But yeah, given the function description, gemstones, we have a string, an array of strings, and we have to return an integer. And it's between 100, and the size of each rock is 100 maximum. So let's go paste the question in here. Zoom in. So we're going to use the very basic example of A, B, C, the one that's given here, A, B, C, and B, C. So if we were to look at it, let's write each letter. So I'm just going to make this a bit bigger. Boom. So A, B, C. Now we could go all the way down to D and then all the way down to Z. However, there's only ABC, so this problem is only ABC. But you would do this for each, or like each integer for each string. So A1, B1, C1. We're here 1, 1, and 1, and over here 0, 1, 1. Okay. So now we need to look. Now the answer will be rows with all ones. So as you can see, this is B and this is C. So the answer is B, C, which is equal to 2. So that is the case pretty much written out, explained how you do the process, and there you go. So now we need to focus on how we're going to implement this. So one way we could do this is we could have a vector, and we can store, or an array I should say, and in this array it's going to be a length of 26, so 26, and this is 0, and then 0, 0, 0, 0, 0, and this can be A, B, all the way down to that. Okay. So what this will do is this will store all the common gemstones in all of them. So obviously, if we try to do each value and the value of each string, at first it's going to be zeros because it's all 0. So a good idea first is to store the values of the first string into that. Okay. So A, B, C. So the values is now going to become A. So the string, or S of 0 become A. Now this is going to be the alphabet, so it's going to contain all the same format like that. And then once we have another string, so let's say we get another string and we get all the alphabet, we get all the characters at 1A, 1B, and we're only setting it to 1 if it exists. We're not doing 1, 2, we're not doing count, we're just going to see 1 if it exists. So we can just do equals. I don't have to do plus, plus, or anything, we just do equals. So we're going to see A1, okay, that exists. So then for each character, what we can do is we can do 1 and 1. Oh, that's true. So the new vector will also have 1, okay? And then the new vector will also have 1 if because they're in common, and all the way down so on. And this new vector will contain all the characters that are similar between this one and this one. So the first and second string. And then we could do this again for the third string, and the third string will have all the characters in common of this one, the third string, second and first string. If you want another way to think about this, think about GCD. The GCD of A, B, and C is also the GCD of A and B, and then the GCD of that with C, because they will have to have it in common. It's like a triple set intersection. However, we have this kind of annoying thing where we're storing 26 integers, and it's going to be quite a lot, and we have to do and 26 times every time. And well, yes, of course you'll pass. Look at the constraints; it ain't that big, and you're probably thinking, why do we have to make it faster? Because this is a really good, easy problem that will allow you to use bitmasks. It's not going to be a complex problem where bitmasks are required, and because they're required and the only solution, you're going to have to know bit. It's a very easy problem where you can do anything, and this way you can experiment with something new. So I'll make a video on bitmasks, but I'll just quickly go through them now. For every character, so for every SI, we're going to have a mask. So we're going to have a S mask, I'll call it. And just going to S for like the string mask. And that's going to be equal to 0, 1, 1, 0, 0. So 1 if the character exists, else 0. Okay. And then finally, we're going to have mask. This is going to be the main mask. And this is going to store intersection / all common so far. Sorry for the writing. And at the very end, we're going to do mask and equals S mask. And this will get the new mask, which would be the intersection. And we do this for every single one. And then afterwards, we return the number of set bits. Okay, so that should be a very basic outline. I will try to explain this a bit more now, and then I'll show you the code of it, which should make a bit more sense. So what we're going to do is we're going to have an overall mask, which will store all the, what this main mask will do, is going to store the letters which are common in all the strings before the one we're looking at. So if we're looking at this second string, main mask will store all the strings common in one, all the letters that exist in one. If we look at the third one, it's going to store all the letters common in the first and second string, and so on and so forth. That's what it's going to store. And this S mask will store all the letters that exist in the current string. And once we have both, and in order to get the intersection, we're going to do bitwise AND on the two masks and store it in the same mask again, the main mask. And this will get the intersection of all the first N strings. And finally, we return, after doing the intersection of each string, return the number of set bits. So let's get coding here. So what I'm going to do first is I'm going to just find n int n equal, let's just help with it, and int mask equals 0. So this will set it all to 0, 32 0, so empty mask, completely fresh. So for boom. So we're going to go for each string. I'm going to set S mask equals 0. Then int m would be ARI size. So this is the size of each string. And we iterate through each string. And then S mask all equals 1 shifted by ARI j minus a. Let's explain this line quickly. Or equals. What does that mean? Well, if you have 2 bits and you have all equals, as long as one of them is true, one of them are true, then the value will be true. So all equals, it will set the bit in SMask, it will set the value, the result of this in SMask, it will set it to SMask. So 1 will always be positive. So wherever this bit is, wherever index this bit is, it'll always set that index to positive for SMask. So how does it work? So the zeroth index will be A, because if we have A minus A in ASCII will equal 0. B will be 1, 2, 3, and this will make 20, those will have 26 bits, with the 25th index being C of the Bitmask. So we do 1 shifted by the distance from A, and we're going to set this equal to true, which means it exists. We're not doing this addition thing, we're not doing that, we're just setting it 1 to true. Okay, and this is in constant time, by the way. I want to point out this is constant time, and we're only using 32 bits instead of 32 times 26, which is not, I'm not going to figure that out in my head. So after we've got this SMask, what we're going to do is if I equals 0, mask equals SMask. Oh. So what this does is if it's the first element, the first string, we're just going to set the mask equal to whatever we have so far, because there is no previous intersection to compare it to. If we did, then we just get a bunch of zeros and the code would fail. So this is going to be the starting point. Otherwise, else, we're going to do the bitwise and of the 2 masks, and this will get the intersection of the 2 masks. So the mask and equals, because we're going to store it back in mask, the string mask. Okay, now after we have done all of this hard and tedious labor, this will result in a bit mask of 1s and 0s, where 1 indicates that the letter exists. So if it's the second index of the mask, that means C exists. If it's the first, it's B, and so on, if it's 1, obviously. Now here is where we are going to show you a cool function that is nice to know and also teaches you more about bitmasks. So we've already learnt we can just set mask equal to 0, that's how you define mask. And in order to set bit true, like regardless of if it's 1 or 0, we do all equals and we do a left shift of 1, we do 1 left shifted by the index you want to shift it by. Here's the final one. I'm going to write this in C++11 format, but in C++20 it's just built in. Oh, sorry, it's just pop count. Mask. I think it might have changed, but I'm pretty sure built-in is gone. If it's not, apologies. But this is how you do it in C++11 format. You do dunder or double underscore built-in underscore pop count, and then the mask you want to pop count. So that's what we're going to turn. If you run the code, hopefully it's correct. Yes, it's all correct. As you can see, pass sample test cases easily. You run this. As you can see, correct very quickly. Very good. This is, well, let's look at this. So this is just going to be in O of n m time, and very low constant factor because it's just O of 1 here. This is O of 1, and bitwise ANDing of 2 bytes or 2 integers is also O of 1. Even though it's doing it each bit, it's still O of 1. That's something you need to know. And also pop count is O of 1 if you're also curious. So this is very O of 1, lovely jubbly. So yeah, that was Bitmask. If I made any mistakes or if you want me to explain anything, I'll try my best, but you can clearly see how a Bitmask can work in this situation. Instead of using an array of integers of 26 integers, like it's going to be a lot of memory. We can reduce that by 32 by simply using a Bitmask, and it will help tremendously. I will also try to post another video where we use Bitmask to enumerate over all possible sets of values and show you how that can be used for complete search problems. But on that, hope you enjoyed and have a good day.